So we're here at the 2013 Planetary Defense Conference in Flagstaff, Arizona, and I'm joined by Gary Hughes, who's an assistant professor of statistics at Cal Poly San Luis Obispo. And I was hoping maybe you could start by just telling our audience what brought you out here to Flagstaff today.
Yeah, thanks. I'm really happy to be here as the Planetary Defense Conference, where people gather to discuss topics related to the impacting of an asteroid on the Earth. So a range of topics. What are asteroids made of? How many of them are out there? How many of them do we know about? How many of them are going to hit the Earth? Can we predict that? So there's a really wide range of talks here, and it's very interesting always, these conferences. So I work with Phil Lubin at UC Santa Barbara on a system called DESTAR. So we brought our poster here to try to make a contribution in that regard.
And can you describe what the DESTAR program is, what the idea is, what the concept is?
Sure. So DESTAR started sort of in the laboratory, where we have some small phased array laser systems that are used to sort of concentrate the power of individual lasers into a single beam, and so therefore become more powerful than any of the individual lasers in the array. And so, you know, since it's a sort of an array of lasers, we could sort of incrementally make those things larger and larger. And, you know, the question then becomes, well, what could you do with a very large system? Well, so in the context of planetary defense and trying to avoid asteroids, if we built a larger and larger system and were able to make it work and deploy it into orbit, you could actually deflect asteroids pretty easily from an orbital standpoint.
Can you describe how exactly you deflect an asteroid? I mean, people might have different ideas in their mind. They might be thinking Star Wars, you blow the whole thing up, you know, who knows what people are thinking. How would this feasibly work in a scenario?
Right, so, you know, the initial idea was to build an array of lasers that's large enough to put a concentrated beam on the surface of an asteroid that would raise the temperature there enough to vaporize materials. Now, what those materials might be, they might range from methane ice or water ice, so you would need to raise the temperature to maybe 100 degrees. Well, for you know, larger objects, you would need to get it a lot higher temperatures, maybe, you know, 3,000 degrees Kelvin or something like that. But once you start evaporating things from the surface of the asteroid, there's a reactionary force. Something that comes off of the asteroid pushes against the asteroid with, you know, a reactionary force that deflects its orbit. So as soon as we can concentrate enough energy on the surface to evaporate things on the surface, we start to deflect that orbit.
So you're basically like creating a jet thruster on the object. Exactly,
that's exactly what we do. And, you know, if you can get it hot enough and vaporize, you know, solid materials, that thrust actually becomes very large.
Is there any quantity of how large you could describe?
Well, so, you know, there's various calculations, but, you know, I mean, if I can get a 30-meter spot to about 3,000 Kelvin, that's equivalent to several shuttle booster rockets.
So compared to other descriptions of, say, gravity tractors or single lasers, which apply a very, very small amount of thrust over a long period of time, this you're actually getting a pretty significant amount of force on the object, correct?
That's correct. That's, you know, if we can build a system that's big enough to actually vaporize the surface of the asteroid, we're creating large amounts of thrust.
And how big of a system, how big would the array need to be you're looking at?
Right. So, you know, then it depends on how far away the object is and how, you know, how long in advance you want to start to attack it. But as an example, sort of the sort of pie in the sky idea that Phil has is his 10 kilometers on a side. The array would be 10 kilometers on a side. And if we could do that, we could put a 30-meter spot on an asteroid that's 1 AU away, one distance, Earth-Sun distance away, and raise that to 3,000 Kelvin. Enough to vaporize something on an asteroid as far away as the sun.
Wow, so it's a very far distance.
Right, well, so that's a big array, right? I mean, obviously we can't just jump in and build a 10-kilometer array. The ones we have now are, you know, 10 centimeters. But, you know, I mean, we're working on a meter-sized systems, you know, working up from there. You know, by the time you get to, you know, maybe 100 meters on a side, you can start doing real work. So.
And this is in the infrared range?
So you can build whatever kind of lasers you want. Our idea is more along the 1 micron range, so 1 micron wavelength in the near infrared. So.
Then we've had obviously a couple attention-grabbing events recently. You had February 15th, you had the flyby of an asteroid, DA 14, 2012 DA-14, which flew between the Earth and some of our satellite systems.
Right.
And then you had the impact, obviously, over Chelyabinsk, Russia, a smaller object, but had pretty dramatic effect. So there's been a lot of attention, and especially on some of these small to medium-sized objects where we might have a shorter warning time. And you had mentioned, we were discussing earlier, you had mentioned that we could actually push one of these out of orbit in relatively close range if it were on an impact trajectory. Is that the case?
Right. So since, if we can build a system big enough to vaporize elements on the surface of an asteroid, we generate lots of thrust, okay?
Mm-hmm.
And so we don't need a year in advance to start trying to deflect the object. We could have a week in advance. For instance, for a 20-meter object like the Chelyabinsk impactor, we don't need, we need a week or less, to get to push that one out of the way. So.
Because a lot of these planetary defense discussions, they talk about years or 5 years or 10 years or 20 years, and some of that focuses on larger objects, but you're looking at a system that could be more of a last minute, so to speak, defense capability.
Right. So we feel there's several advantages to DE-STAR, and one of them is that, if you could build such a system and put it in orbit, it would be there at the ready. Mm-hmm. You wouldn't have to think about a dedicated mission to an individual threat. As soon as you found a threat, you could instruct the system to attack that threat at a moment's notice, right? Mm-hmm. And so it would be on the ready there in that sense. Beyond that, we also think that there's other things that you could do with such a system.
Right.
So it wouldn't be just a planetary defense system, but you could, for instance, if you had enough energy to vaporize the surface of an asteroid, you would then be able to look at the heated spot on the asteroid, and the plume coming off of it would absorb radiation, characteristic radiation, so that you could see the absorption lines from a telescope on Earth and actually determine the chemical composition of the asteroid. It's one of many other sort of potential uses for such a system if we could build it.
Mm-hmm. And is there any other applications for things like space debris? Is obviously a big concern that's grabbing a lot of headlines. Worry about satellites getting hit with pieces of junk, and even some relatively small pieces can cause dramatic damage. So would this be something that could potentially help with that concern as well?
Certainly, since it's a phased array, we can point it pretty accurately in any direction that we want, and so we could point it at an orbiting piece of space debris and heat it up to the point of vaporization and knock it out of orbit very quickly. So even large pieces of space debris we could knock out of orbit very quickly.
Right. Well, it sounds like a very interesting and versatile technology that we could use for defense, but also science missions, so it sounds very interesting. I don't know if you have any other comments for our audience on the importance of this project or anything else?
So there are other uses that we envision as well. Like you could use it for sort of interplanetary propulsion of a spacecraft, right? So, if a spacecraft gets up there and wants to fly to Mars, you need to, have some propulsion system aboard. So you need to either carry the energy on board, or you need to, give it some energy on its way. DE-STAR could be used for something like that. So, it kind of provides some tantalizing capabilities for interplanetary, and maybe even if we could build a big one, interstellar travel. So if you provide continuous acceleration over, some period of time while an object is in the solar system, we could get it going pretty fast.
Right.
So,
which would be basically a game changer for our space exploration, because if people think of the shuttle, most of the mass of the shuttle was fuel. You had those huge booster rockets, and all the fuel you take, you got to lift up and carry with you.
Right.
So you're talking about a potential of keeping that, removing the need to take that fuel source with you.
Exactly.
And be able to transport the energy to the spacecraft.
Exactly. Right. So, there's a whole range of things that could be done with a sufficiently sized DE-STAR, and I think that's one of the main benefits that such a system would provide over sort of dedicated missions to an individual threat. So.
And technologically, is this something that would require huge developments, or is this technologically feasible? Is it just a question of cost, or is there some new breakthroughs that would have to be made to develop such a system?
So, in our initial sort of thought about this, we have desktop versions of phased array lasers, and our initial thought was to take those and, increase them in size to a system that we could then deploy. So I think the science is pretty much settled, right? But there would be technological issues to making a larger and larger system. So the idea of a phased array is that the wavelengths are all controlled very tightly as they're being emitted from each laser. And so as you make a bigger and bigger system with, sort of vibration in a structure might affect those wavelengths. You know, so I think there will be some technological hurdles, but I don't think that there's any scientific hurdles, right? I mean, the theory is sound. We know that it works. We have them in the laboratory. So we need to develop a little bit of technology then to scale up.
Well, this is definitely a very exciting prospect, and I hope that you guys can get more support and continue the investigation, hopefully see some systems like this up there, defending us all from these rogue invaders and giving us better scientific capabilities out there. So,
well, thanks very much. I appreciate your interest in the DESTAR.
Sure. Thank you for talking with us, and thank you from Flagstaff.